the mechanical curve or input and electrical curve output. Then also sense the significance of this J, which is actually the moment of inertia. Then this T is time, but we haven't yet discussed this theta. What is this theta? Just saying that this is the rotor angular position or rotor angular distance. But we haven't seen any formulation for this theta. So today actually we will the rotor angular distance. Okay. So today actually we will discuss this parameter, what is theta m, and how we can actually calculate the theta m. That is we will discuss in this next two slides. Okay. So now at this from this slide. So the first point is that the angle theta m is a mechanical quantity. So this m here represents the mechanical quantity. Okay. Representing the rotor angular position measured with respect to a stationary reference frame. Okay. So this is the rotor angular position which will be measured with respect to a stationary reference frame. So this is our stationary reference frame which will be fixed here over the time. There will be no movement of this frame, and this is our rotor position. Okay. So we know that in equilibrium state or in the steady state, the rotor rotates at synchronous speed, right? That is the ns of the fixed speed. And if there is any disturbance, maybe rotor will rotate in another speed rather than the synchronous speed. But in all the time, actually rotor will rotate. It will not be fixed. It will not be actually at distant speed, right? That means that this rotor position will be changing over the time. Let's say this is the moment when time t was to t1. Okay. Now we are measuring this theta m with respect to this stationary reference frame, and we are getting this amount of theta m. Now let's say after a certain amount of time, like t was to t2, our rotor is now here in this position, right? So what will be the theta m now? It will be from here to here, right? Always theta m will be the difference between the rotor position and the stationary reference frame. So we can see that this theta m is an ever increasing parameter, right? It is always increasing with respect to time. Let's say after completing one cycle, it will come here and it will be aligned with the stationary reference frame. At that time, theta m will be fixed steadily. After then again there will be movement. So if after completing one cycle, if the rotor position is now here, again we will say that this is actually the theta is theta m plus the previous 360 degree into one complete cycle, right? So like this way, this theta m will be increasing over the time. That is the basic takeaway from this slide. That actually what theta m is not a fixed quantity; it is actually changing over the time. Okay. So we can actually take one example which we actually make this concept more clear. Let's say this is one stationary reference frame and this is a ball. So this frame is fixed here. There will be no movement from this position from this frame. And in this ball we have applied some external force F. And for this force, the ball is still moving in this direction with a velocity of v. Okay, let's see. So if now I want to measure the distance between this reference frame and this ball, let's say the distance is represented by v. Okay. So over the time, this v will be increasing, right? Because let's say there is no friction here, so the ball is moving at a constant speed v. Okay. So if we want to measure the distance between this frame and this ball, so with respect to time, t will be increasing continuously, right? Now this type of parameter, which is actually the ever increasing parameter, if we keep this parameter in our equation, then actually sometimes solve. Okay, because whenever we will solve some numerical problems, we can determine the exact value of this theta m, okay, whenever needed. That's why somehow we will replace this theta m with some constant parameter. Okay, for that portion we will need we will need another concept. So let's say instead of using this stationary reference frame, we are using the moving reference frame. So this is another reference frame which is actually moving in this direction with a velocity of v. Then let's say this is our ball. Okay, so if we apply external force, so there will be movement in this side, and let's say the speed is v. This is the constant speed at which this ball is moving. Okay, so also this rotating frame, actually the moving frame, okay, is also moving in this side with a velocity of v. Now if we want to measure the distance between these two, let's say this is the d. Now can you say with respect to time will there be any change in d? It will be a fixed quantity, right? So using this concept we can actually make this theta m fixed. Okay, so this concept will be used in this slide. So it is written over here that to make the angle theta m constant in steady state, means the rotor will turn at synchronous speed. So to make the angle theta m constant in steady state, we can measure this angle with respect to a synchronously rotating reference frame instead of a stationary reference frame. Okay, so previously we had this stationary reference frame, but now we are using additional reference frame which is actually synchronously rotating. Okay, and here the speed is omega m, which is actually the synchronous speed, and m for the mechanical quantity. Okay, so s for the synchronous speed, m for the mechanical quantity, because we are now in the mechanical model, right? That's why all our parameters will be in the mechanical model. So now this frame is rotating at the synchronous speed omega ns, right? And this is the rotor position. Okay, this is also rotating. Okay, so let's say we are talking about the steady state condition, right? So at steady state, the movement or the speed of this rotor, that is omega m, will also be omega ms, right? So these two, rotor and this frame, actually are rotating at the same speed. At that time, this distance, delta m, the distance between this rotor position and this rotating frame, will it be a fixed value or will it actually vary with respect to time? It will be a fixed value, right? So delta m will be fixed. Now there is theta m, which is actually the distance between rotor and the stationary frame. Now we have actually introduced another quantity, that is delta m, which is the distance between the rotor and the rotating frame. Now somehow we have to replace this theta m with the delta m, right? But before that we have to build up some relationship between this theta m and delta m. Okay, what is this? Using this, okay. তোমরা ক্লাসের যে সিকোয়েন্স আছে না, ক্লাসের সিকোয়েন্সে এই একটু ক্লাস করতে দেখতে পাচ্ছেন না? If you can go outside and talk, okay, after finishing your talks, you can come in inside. You know, we don't need to কথা বলছিলাম আমার সাথে। If you have any important talks, you can go outside. Okay? Then after finishing the talks, you can again come inside. No problem. There will be some problem because if you continuously go outside and come inside, it will create some problem for me. Okay? So what you can do, you can go outside, you can block whenever my lecture finishes. So whenever I return to your office, you can come to this. I can place responsibility at this, I can give the reference. But do not make any noise. So now let's try to build some relationship between this theta m and delta m. Okay, how? So let's say this is the rotating frame, right? So at time t equals to 0, this rotating frame was actually aligned with this stationary frame. It was in this position. Okay, and with the increasing of time, it is actually rotating, right? Let's say it is clockwise. There. So at time t, what will be the distance covered by this rotating reference frame? Can you determine? It will be the speed multiplied by the time, right? So what is the speed of this frame? Omega ms. And at time t, it will cover omega ms multiplied by t distance. This amount of distance will be covered by this rotating frame. Okay. So with this term, we can easily know the rotation of our rotating reference frame with respect to this stationary frame, right? Now,
we are considering omega ms t. Why are we considering their because and they with the same thing because this is the synchronization current. They are on the same phase.
this. Oh, okay. So let's say we started our analysis a bit later. Okay. Then there will be some phase difference like this. Okay. So you are talking about this rotor and this rotating frame can start together, right? So there will be no phase, no delta. Not like that. Just think that there is some phase difference between this. Okay. Because all of our this frame are actually the imaginary frames. Okay. There is no frame with the generator. Okay. So by this term, we are actually locating the rotating reference frame, okay, into some position, and from that position, if we add this value, this delta m, we can know the rotation of this rotor position, right? So simply this theta m, which is the distance between this rotor and this stationary frame, it will be equal to this term. This term we will calculate this amount of distance plus this delta m. That will be our theta m. Okay. So have you understood this formula? So this is
angular velocity is same formula. Angular velocity stationary rotor আর হচ্ছে synchronously rotating reference frame. Similarly, omega m or omega ms.
no, actually it's not necessary to actually have this value omega m always equal to omega ms. Okay. In steady state or in equilibrium state, we can say that this omega m equals to omega ms. At that time, there will be a fixed value of delta m, right? But if there is any disturbance, obviously this omega m will not take the synchronous speed. Rather than it will take another value, right? At that time, there will be some variation in this delta m. Okay. So we will consider that part as well in the next slide. Okay. So delta m is omega ms t plus delta m. Now to replace this theta m by the delta m, we have to double repeat this formula so that it becomes t square theta m divided by dt square. At that time you can replace this whole term with the term of omega delta m, right? So the rotor position, then we will get the angular speed of the rotor. Okay. So we will do omega m equals to omega ns plus g delta m divided by dt. Okay. Now if we just take this term on the left side, so in the right side we will have omega m minus omega ns. Okay. Now
Sir, omega ms is a real synchronous being here.
omega ns is the synchronous speed. Okay. Synchronous speed, but m is the mechanical quantity. Okay. Then this equation we have to do the derivative again. Okay. At that time we will get d square theta m divided by dt square, which will be equal to, this term will be vanished because this is a fixed value, right? Constant value, and it will be d square delta m divided by dt square. Okay. Now look, this term can be replaced by this. Okay. So what was our dynamics equation? It was like this. So now this term will be replaced by d square delta m divided by dt square. Okay. So this. So now this is our updated dynamic equation. Now in this equation, look, these two are actually the torques. These torques are actually maybe the mechanical quantities. So we started our explanation with the mechanical model, and we told that actually we will gradually shift to the electrical model. Okay. So that's why now we will multiply omega m in the both sides so that we can convert it from torque to power, because power is the electrical quantity, right? So by multiplying this omega m in both sides, we will get this equation from this. Okay. So multiplying this Tm with omega m, we will get the Pm, that is the mechanical power input, and this will be the electrical power output, Pe. Okay. And this side will be simply j omega m d square delta m divided by dt square. So any questions up to this?
Sir, omega m is omega m is
Omega m is the speed of the rotor. Okay. And this is not a fixed value. In steady state, it will take the omega ms, but during the disturbance, during any fault, it will take another value. Okay. So this we can be sure that this will be a fixed value. But for this omega ms, this is a fixed quantity. Okay. So this is constant. That is the synchronous speed ns. That is equal to 1 to j power. Yeah, I already explained that part. Actually, there in steady state, this omega m will be equal to omega ms. Okay. At that time, this omega ms and this omega ms are same. So their time will be constant value. So in that case, it will be 0. Okay. But they have different scenarios. Like our system is contaminated with some fault or disturbance, right? At that time, this omega m will take another value rather than this omega ms, right? At that time, there will be some changes in delta m. Okay. So that's why we are keeping it like this, so that this equation can be applicable for both the steady state condition or the dynamic condition. Okay. That's why we are keeping it like this. Any questions?
As we know, the rate change of omega ms decides the rate change of delta m. Like if omega ms changes, then delta m also changes. So when we are taking 0 for derivative of omega m, why we are keeping it for delta m? Like the derivative of delta m might be given in the equation, but for the derivative of omega m, that will make it change to 0. I mean, when we are taking the derivative of delta m, d delta m by dt, you said that
This thing, right?
yes, you said that it can change when there is a disturbance in the system. D delta m by dt, it can change. But when we differentiated for the second time, we took the derivative of the omega m to be 0. But we know when omega m changes, that's the time when delta m changes, right? So if one is not 0, then how can other become be 0?
Yes,
যে ওমেগা চেঞ্জ হইতেছে তাহলে আমরা কেন এটা কিন্তু ডেল্টা এমএরটা ধরতেছে জিনিসটা জিনিসটা একটা
Actually, this question was that why during the double derivative we are taking it as constant and we are making this term 0. Okay? Because this is omega ms, not omega n. Omega n may change, but omega ms is a fixed term. Omega ms is the synchronous speed, okay? But in mechanical domain. And omega n, this is the speed of the rope. Okay? So this can change depending on the disturbance. But this omega ms will be a fixed term. Okay? So that's why whenever we are doing the double derivative, so this term are getting cancelled. Okay? You understood this thing?
Sir, ये reference frame में दिया speed को इससे synchronous speed है जैसे always करते हैं
And this, the speed of this rotating frame will also be the synchronous speed.
हाँ सर rotating frame चाहिए ये आप move करते हैं तो synchronous speed move करते हैं सर rotating frame चाहिए हमें move करते हैं तो ये तो synchronous speed always करते हैं ना ये तो value को चेंज करते हैं
Now, it আমরা ধরে নিচ্ছি যে এটা আমরা synchronous speed এ move করব। So the speed of the rotating frame will always be the synchronous speed. Okay? It will be always constant. That we are assuming. Okay? Okay, now from this line to the next line, we will multiply half. Actually, this j is not here. So we will multiply half omega ns in both sides, and then we will divide the integral equation by the base MDA base. Okay? So look, previously it was like this. Okay? Now after multiplying, we are getting this extra term half, this omega ns in both sides. Okay? Then we divided the integral equation by this base. That is the base MDA. Okay? Now we can define the new parameter, which is actually h. Okay? What is h? H actually is half j omega ns square divided by s. Okay? So this is the h. So what is h actually? H means the inertia constant. And j is the moment of inertia. These two are not same. Okay? These two are related because from this equation we can see that h is depending on this value j term, right? So you can say that h is a function of j, but these two are different. These two are not same. Okay? H is the inertia constant and j is the moment of inertia. So by looking at this term, can you say that this actually quantity is this half j omega ms square? Actually, this is the kinetic energy, right? Like half mv square. Okay? And this is the base mv. So what will be the unit of h? It will be the unit of energy divided by the unit of base mv. That is the mv in the below side, and in the upper side it will be megawatt second. Why? Because the energy of work is actually equals to P multiplied by T, power multiplied by time. So in that sense, it is actually megawatt second divided by MV. So this is a Newton means MV means this is the base apparent power. Okay, MV. The basic unit is VA. And to other apparent power,
voltage पे
yeah, actually voltage. From that power, we get the this is the S. And to one this thing is V. This is the base MVA is MVA unit. Now in the next line, actually, as you can see that h is actually half j omega s square, right? But in this equation we have j omega m multiplied by omega ms, right? So here we will use some kind of assumptions like the variation of omega n and omega ns is very less even during transients. Okay? So during the steady state or equilibrium, obviously this omega m equals to omega ms, right? But in transients, the omega m will vary from the omega ms value. But approximate omega ns as omega n. Okay, which will give us this. Okay, that is the half j omega n omega ns is approximately equal to half j omega ns square. Okay, now in this equation it will be half j omega s square, right, divided by s a. This whole term can be represented by this a for the inertia. Okay, that's why it is written over here like this a is then d square delta m divided by dt square. So a is d square delta m divided by dt square. So right side is same as before. Okay, this was the previous equation. So here we are assuming this omega n equals to omega ns. So it will be j omega ns square, then this is divided by sd. So this term is actually the h, right? So we can write it like this whole term is h, then d square delta m divided by dt square equals to the right side is actually same here. Okay, understood? Now this term pm divided by sd and pe divided by sd, you can write it as per unit. Okay, because we know that whenever we divide the actual value with the base value, then we get the per unit estimate, right? So actually, intentionally we divided SB here. Okay, to make our calculation per unit here. Why? What is the benefit of per unit value? Can you say why do we want to calculate our parameters in per unit estimate? Is there any benefit of per unit value?
Ratings are always given.
Well, ratings are always different.
The ratings are always given in this page.
Another, what is the benefit of this per unit estimate?
So when we are transferring the machine from one facility to another facility, the base values or the password values they may not be same. So when we are connecting it again, if you don't use the binary system, we have to calculate everything of that system. But if we know the binary values of that machine, then we can normally get the new values from the old partition.
Actually, we have different voltage levels throughout our power system network. Okay, we may have 11 kV or 132 kV or 400 kV as our voltage. Okay, so but if we calculate all the parameters in power unitized value, then it is easier for us to compare different parameters. Okay, so let's say we are saying that our V is 0.8 per unit. Okay, that means the actual value of V is the 80% of the rated value. Okay, the rated voltage, regardless of the system. So whether it is 11 kV system or 132 kV or 400 kV system, 0.8 per unit means our actual V value actually was 80% of the rated voltage. If the rated voltage is 11 kV, then this 0.8 per unit means the 80% of the 11 kV. Okay, that is like this. Also, there is another benefit. So actually, when actually we do any power system optimization research, we have to generate some objective function. Okay, or it is called the fitness function. Okay, the objective function. At that time, we have some parameters, like let's say A is one variable and B is another variable. Okay, so combinedly we want to, let's say, minimize or maximize this variable. Okay, that is the optimization. So we want to optimize it as the maximization problem. Okay, let's say we want to maximize this two variable. So whenever we do the summation, let's say this is the power quantity and this is the voltage quantity. Okay, the unit of power is megawatt, while the unit of voltage is, let's say, kilovolt, right? So can we add these two? We can add, right? So if we convert this power value in per unit value and voltage in per unit, then we can add. Okay, we can add, and finally we can maximize this overall term. Okay, so that is one kind of benefit in the per unit calculation. So So here actually by dividing this PM by SB, it will be PM per unit, it will be PE per unit. Okay. Now this is the updated version of our equation. In this equation, the delta M and the angular respect to omega M is both are actually the mechanical quantities. Okay. Because M is written over here, right? So now we need to convert those into electrical quantities because we want the electrical the system. Okay. So how to convert these quantities from mechanical to electrical, that things will be discussed in the next two slides. Okay. Before that, if you have any question about this, you can ask.
Sir, okay, let's go.
Yes. Actually, I am saying that let's say we are doing one this stuff. Why actually you want to let's say minimize. Let's say minimize this easier for me to take one example. Let's say I want to minimize the P loss, the power loss, and the voltage. Okay. Actually, in practical scenario, always the voltage gets increase. Okay. So minimize means that to keep it around 1 per unit. Okay. So in normal scenario, maybe it can increase from this nominal value. Okay. So that's why we are treating this as minimization problem, that we want to minimize this. Okay. It doesn't mean that we will minimize it to 0 per unit, not like that. Okay. So minimization value means that we will try to keep it around 1 per unit. We will not allow that much increase from this 1 per unit. Okay. So if we do this, so the unit of P loss may be kilowatt or megawatt, and this voltage may be in voltage or kV unit, right? So we can directly add these two because these two are different units, right? So what can we do? We can take one base and then we can divide these two. We can convert these two into the per unit as well. Okay. Then we can add, and then we can combine the solve the minimization problem. Okay. So this is the basic. I faced this issue in my past journal paper. I submitted, okay, then the reviewer said me that these two are in different units. So how can you add these two and minimize it? Okay. So at that time, actually, this concept actually came to my mind. Yeah, okay, so you can show the per unit. Okay. Then we actually corrected our calculation and we converted these two per unit terms. Then we had, okay. Then we actually defined this system to the regular and we accepted it. Okay, now it's like this. Now, any question? Any other question?
Sir, in dot u or q, it is mechanical power or it is electrical power?
Exactly. So this is the mechanical power by unit value. This is the electrical power by unit. Now let's go to the next slide. Let's think about the two-pole system. Okay. So this is the two-pole system. Means that there is one north pole and one south pole. Okay. So normally the number of poles actually become even numbers. Okay. So either it is two-pole system or four-pole system or eight-pole system like this. Okay. So there will be always some pair. So two-pole system means one pair pole, one north and one south. Okay. Will form one pair. So there are some magnetic flux lines, and we know that actually magnetic flux lines originate from the north pole and it actually goes to the south pole, right? And so these are actually the direction of the magnetic flux lines. Now there are two poles, north pole and south pole. This circular one, this is the rotor, okay? And this one is the conductor. Normally the conductors are mounted over the rotor. So if we this is actually the cross section view of this rotor and this conductor. So if you take this cross section view, it will look like this. Okay. Now, can you tell me that between this conductor and this rotor, which one is actually moving? The rotor will move actually, right? The conductor will be fixed, right? So we can understand the same scenario in the reverse manner. Like we will assume that this rotor is fixed and this conductor is moving. It is the same thing actually, right? Can you understand this thing? It's the same thing. So we will actually apply this technique that we will assume that this rotor is fixed and this conductor is traveling across this rotor. Okay. So which will actually make our understanding very much clear. Okay. Now we will measure both the mechanical distance and the electrical distance. So first let's measure the mechanical distance. Okay. So for measuring the mechanical distance, we do not need to think about the poles or the magnetic flux lines. Okay. Mechanical distance means the measurement that actually we do in our day-to-day life. Okay. So let's say if I tell you that what is the distance between me and that door, so you will say that let's say it is 5 meters. Okay. So actually this is the mechanical measurement, the mechanical distance. Okay. So the by default our brain actually thinks about the mechanical distance calculation. Okay. So whenever we will measure the mechanical distance, we can simply draw one rotor and one conductor. So no other poles and magnetic flux lines are needed for the mechanical distance measurement. Okay. Now let's say at time t equals to 0, our conductor is here. Okay. So it is now traveling across this path. So whenever it will come here, okay, can anyone say how much mechanical distance will be covered from this to this
I by 2.
in terms of degree?
I by 2.
It will be 90 degree, and in terms of area it will be pi by 2, right? And whenever it will come here, so from this point to this point, how much mechanical distance is covered?
By
Pi or 180 degree, right? Then if we complete one cycle, so from here to here again,
twice time.
what will be the mechanical distance? It will be twice pi or 360 degree, right? So this is the theta m or the mechanical theta. Okay, mechanical angular distance. Now let's think about the electrical distance. Okay, so to measure the electrical distance, we have to consider the poles as well as the magnetic flux line. Okay, so let's say now at t equals to 0, our conductor is situated here, which is just at the middle of this north pole, right? Where this is the where actually maximum flux lines can cut through this conductor, right? So this is actually the maximum flux point. Okay. This is okay. Whenever it will come here, there will be no flux lines cutting through this conductor, right? So the magnetic flux will be 0. Again, whenever it will come here, it will be again the maximum, right? But in this two, both are maximum. But look here, the conductor will feel that the flux lines are coming into it, right? Like this. And in this position, the conductor will feel that the fluxes are actually going out from it, right? That means these two magnetic flux will be actually opposite, right? If we assume one is positive, another should be negative, right? So we are assuming this point as the positive point. So here, let's say actually here this is this point, okay? This point, the maximum magnetic flux are in the positive side. And whenever it will come in this side, it will be again the maximum but in the negative side. So this is this point, right? So from here to here, we know that the mechanical distance is pi or 180 degree, right? But in electrical distance it is from here to here. So can you calculate this distance? How much this is this? This is the pi, right? Or 180 degree. Okay. Again, if it comes from here to here, again it will reach the maximum positive, right? Like this. Okay. So again from here to here it will be 180 degrees or pi, right? So for the electrical distance from here to here for one complete cycle, how much electrical distance will be covered? 180 plus 180 or pi plus pi, 2 pi, right? From here to here, right? 1 pi. This is actually these are in this distance, right?
It's 180.
This is 180, exactly. So this is 1 quarter, right? So one side, right? 1 quarter means 90 degree. 90 degree, then again this is another quarter. So 180 degree, okay? So from here to here, if it comes from here to here, then that means in electrical degree, the electrical distance is coming from this to this, right? So this will be another 180, right? So in complete one cycle, it will be 180 plus 180 or twice pi, okay? So what is the electrical distance here? Twice pi. What is the mechanical distance? Twice pi, okay? So for two-pole system, theta E equals to theta I, okay? Now let's increase the pole number and let's think about the four-pole system. Here the number of poles are 4, okay? So north, south, like this. So first, let's talk about the mechanical distance. So this is our conductor at t equals to 0. So if we think about the mechanical distance, if it travels one complete cycle, what will be the mechanical distance? Twice pi, same as before. Is there any difference for mechanical distance? No, actually it will be same, right? Because it doesn't depend on the number of poles or the magnetic class lines, right? So it will be simply twice pi here as well, okay? But now I want some answer from you, okay? Let's say the conductor is here, right? That means this point, okay? Now let's say it is coming here. Can anyone say how much electrical distance will be covered? It will be? Yeah. One says that it is 90 degrees. So 90 means the mechanical distance. Okay. But in electrical distance, actually, this is one maximum point, this is another maximum point.
180.
So this is not there, right?
180.
So what is the electrical distance? 180, right? Then from here to here, it is coming from this to this, right? So another 180. Then here to here, from here to here, this is another 180, right? Then here to here, that is this point is another 180, right? So if we add up all for one complete cycle, we will get theta E as how much pi? In terms of pi, we will get 4 pi, right? Because there is 180 is 1 pi, 2 pi, 3 pi, 4 pi. Okay. So we are getting theta E as 4 pi. And in mechanical distance, we are getting twice pi, right? Now how can we write this two things? Our theta E is now twice of theta E, right? This is for t equals to 4 or for four-pole system. For two-pole system, theta E was theta I, right? So this is actually the t equals to 4. Now from this two equation, can we formulate one general expression between this theta E and theta N? We can do, right? Because here the multiplying factor is 1 and here it is 2. Let's say this is actually the 2 by 2, right? And let's think about this as 4 by 2. 2 by 2 is 1 and 4 by 2 is 2. Okay? That means the lower term is same, that is 2. And actually the upper term represents the number of poles, right? So we can write theta E equals to p by 2 theta I. Any conclusion here? This point, right? Look, for two-pole system, theta E equals to theta I, right? For four-pole system, actually it is twice theta I, right? So here it is 1, right? So we can write like 2 by 2. We can write, right? And here it is 4 by 2. Okay? So this 2 is fixed. And what is this 2 and 4 is? Well, this is changing due to the number of poles, right? This is actually the P. Here it is 2 because this P is 2, right? And here the P is 4, that's why it is 4. Okay? Understood? So
twice by 2, so if the twice by 2 I understand that because today this 4 pi electrical distance and mechanically twice.
এখান থেকে তো এটা হচ্ছে twice pi, এটা হচ্ছে 4 pi। এখান থেকে তো লিখলাম হচ্ছে theta E equals to twice of theta I। তাহলে so then we can finally write this expression like theta E will be equal to p by 2 theta I, right? So short conversion of mechanical to electrical is done, right? So for delta m is the mechanical delta and this is the electrical delta. So there is no need to write the subscript E because as an electrical engineer we will easily understand that this is actually the electrical delta. Okay. So now we are into our domain. Okay. So let's say this is the electrical delta and this is the synchronous speed in electrical domain and this is synchronous speed in mechanical domain. Okay. So delta will be P by 2 delta S and omega S will be P by 2 omega S. So you understood this thing? For the previous expression, our electrical quantity will be equal to P by 2 of mechanical quantity. So that's why this is electrical quantity P by 2 mechanical quantity. Electrical P by 2 mechanical. Okay. This is the thing. Now previously our equation was this. Is d square delta m half omega minus m per unit minus d per unit. So here we will replace this delta m and omega minus with this delta and this omega s. Okay. So from this we can write delta m as 2 delta by p, right? We are taking this p by 2 in that side. So we will get this thing. So look, this delta m is replaced by 2 delta by p. And this omega minus is replaced by 2 omega s by p. So this 2 actually if you cancel out, we will get d square delta by dt square omega minus divided by 2s pm per unit minus p per unit. Okay. And this is the final form of our desired swing equation. Yeah. So from the last class till now actually we were looking for this equation. Okay. So this is the desired form of our swing equation. By looking at into this equation, can anyone say that which type of information actually this equation is providing to us? For the rotor, which type of information we can get? This is actually the acceleration, right? That means the swing equation actually gives us the information of rotor acceleration. Okay. Actually, this is the physical explanation of the swing equation. That gives us the information of rotor acceleration. Okay. Now, in steady state, actually Pm should be equal to P. Okay. In steady state, it should be the case. In steady state or in equilibrium, Pm should be P. So here the difference will be what? Pm minus P. In steady state, the difference will be 0, right? In steady state, it will be 0. Okay. That means we will not get any term of or d square delta by dt square. Understood this thing? That means there is the acceleration associated with the rotor because rotor is running at constant synchronous speed. Because now we are in the steady state. Okay. At that time there will be no change in delta. Whenever our system is running at steady state or in equilibrium, will there be any change in delta? No, there will be any change, right? That's why in steady state we can write our Pm actually this is the true for steady state condition. Our Pm should be equal to P. So at that time we will get 0 value for the acceleration. That means there is no acceleration associated with the rotor, which means that rotor is rotating at synchronous speed, which is a fixed constant speed. Okay. So any other question?
Angular acceleration.
Yeah, actually this is the angular acceleration. The Javelin rotating of this is will give us the acceleration, right? So this is actually acceleration can be found as this is the rotor acceleration. Now, when we will solve some numerical problems, we have to take details of the numerical methods, like the Euler's method. Okay. Can anyone say that what is the order of this equation?
Second order.
This is actually the second order equation, right? How can we determine? We have to look at the maximum number of derivative inside the equation. It is true. That's why the order is true, right? So when we will solve our problems using this Euler method, so it's difficult to handle the second order system. Okay. So what can be the option? We can split this second order system equation by two first order equation. Okay. Because there is only one second order equation, it can be split easily into two first order equations. Okay. That is done here in this slide. Okay. What is the first order equation here? This. Okay. From why we are getting this? In any of our previous slide, we wrote this term T delta m divided by dt equals to omega m minus omega m, right? So this term here actually is again written, okay? T delta m divided by dt omega m minus omega m, but here the quantities are in mechanical domain. Now we know how to convert this, right? So simply by 2 delta by b here, for this 2 omega by b, for this 2 omega m by b, okay? If we get this 2 by b common here, then this 2 by 2 will cancel out by this. So finally we will get this, okay? This is our first order equation number 1. Okay? Another first order equation, we can do the second derivative of this equation, okay? It will be d square delta by dt square, okay? And it will be like only d omega by dt, right? Because this term will be vanished. This is a fixed constant term, right? So it will be like this: d square delta divided by dt square equals to d omega by dt. Okay? Then this value is equal to this value from our solution, right? That's why we are just taking this value. So now this is our another first order equation. This is the summary that this is for actually the first order equations which actually can split from this single segment equation. Okay. Now while solving our problem, we can use these two equations. So we will make our